So we're looking at page 29 here, involving contingency tables. Generally, we use conditional probability to handle these sorts of situations. We have a rule here. Probability of B given, so that vertical line there means given, A has occurred, is equal to the probability of A and B over the probability of A. All right. So we have to look at the two events and on the top, see where they coincide, and then divide it by the probability of the given value. So B given that A has occurred. All right. So when I say probability of B given A, it's really a directive. Find the probability of getting B given that A has occurred. All right. So in the case of number one, following the formula, I would call pass the B and female the A. So if I'm applying my rule, I'm looking for the probability of female and pass over the probability of female. Now there is a shortcut to what I'm about to show you, but I figured show it to you the first time, get a good feel for it, and then we go from there. All right. So for the top, we'll just focus on the top now. The probability of female end passing. Use my highlighter, handy dandy. Here's female and any instance in which the individual passed. So that's all of these folks. All right. Now this would be all out of the grand total. So I'm going to do a 157 plus 61 plus 46, 33, 18, and another 13, I believe. That's 328 individuals out of 653. Oops, I don't need to close paren. Then on the bottom, I'm just looking for the probability of female just in general. All right, so this is the number of females out of the grand total, 365 out of 653. In a complex fraction, if there's a common denominator, complex fraction is just fraction over a fraction. If there's a common denominator, you can cancel them out. If there's a common numerator, you can cancel them out. But in this case, common denominator. So we have 328 over 365. If you'd like the decimal form, it's about 0.899. So roughly 90%. Okay. Now, the shortcut to it. It's more of a hand-wavy, verbal way of handling it. But if I look at female is the given. All right, so I'm just going to kind of tuck this off on the side. Female is the given. That's not my marker. Let me get rid of this. It really just means ignore the rest of the table except for the given. If I tell you that it's a given fact that the individual is female, then I don't care about the males. All right. So female is the given. There's 365 of them. From what I just encapsulated, and what I just shaded, from just that column, I'd be looking for the probability that the individual earned a passing grade, which is everyone except for these 37 individuals, right? Which gets you to the 328. I'll show you, in number 2, I'll show you just using the shortcut. So the given is male. All right, these tables here are actually for these problems, so I guess I could just kind of move this down here. So if I'm looking for the probability that the individual will fail given that they're a male, so the given is the male category, of which there are 288 individuals, 59 of which failed. So 59 out of 288, about 0.205. All right, I put these little tables here so that you can mark them up. I think makes it a little easier to understand. All right. The next one, actually numbers 3 and 4, kind of a little bit of a twist on this concept. So it says, is the probability of a given male, all right, so I'm just going to kind of look at this off on the side, a given male. So here's my given. Is that the same as the probability of male given A? All right, so the A here is the given. So it's basically 2 problems in one. So in the case of male, again, just put that in there. Out of the 288, because that's my given, only focusing on the 288 males, how many got an A? That would be right here, the 90. All right. Now the other one changes our perspective. So now the given is whether a student earned an A. All right, so that's my given. I'll change color on that. All right, so my given is whether or not the student got an A, of which there were 247 individuals. $90 of which were males. All right, so they're asking, are these 2 probabilities the same? Well, they're fractions that have the same numerator but different denominators, so they couldn't be the same, but just in case. About 0.313. And then for this one, so 90 over 247, about 0.364. All right, so no. Not too far off. As I've collected this data over the course of 20 some odd years, there was a lot of variation early on, but now it's sort of settling into what it really is. So these numbers weren't really close, let's say 15 years ago, but now they are close. So I would imagine 20 years from now, they'll be even closer. Maybe even next year, who knows? Now, number 4, I put the recall statement in there. Probability of B, if probability of B given A is equal to probability of B, then A and B are independent. That was a statement on a previous page that I kind of glossed over, so you're forgiven if you did not immediately and instantly recall that. But that is a rule. If that relationship is true, then we know the events are independent of one another. So, using that information, it says attempt to show, we don't know that it's actually going to be true, that being male and getting a B plus are independent events. All right. So I could designate whichever one I want as the given. For these kind of problems, I tend to do it both ways. So I'll find probability of B plus given that the individual is a male. And then we'll find the probability of male given that the individual earned a B plus. So it's essentially the same kind of question as what we did previously. All right. If the probability of B plus given male is the same as the probability of B plus, so this is the twist on it, and the probability, I'm going to try to move some of this over here for a sec real quick. And the probability of being a male, given that you got a B plus, is the same as the probability of being a male. All right, so this is an and situation. I'll put a little ampersand there. If they're both true, then the events are independent. All right, so a little more table work here. Again, this is my given. So from the set of males, getting a B plus right there, 59 out of 288. Probability of getting a B plus in general, regardless of male or female, that is 120 over 653. All right, so I'll run those numbers, 59 over 288, 120 over 653. These numbers are in the same neighborhood, but they're not exactly the same. They're not quite the same, so I'll say not equal. I'll make a little note down here. It's about 0.205. 0.184. All right. If it doesn't work for this, kind of like the empirical rule, if it doesn't work for this, then we don't even bother doing this. All right. But since this is instruction, I might as well do it. Instructional, I should say. So here's my B plus given. All right, probability of being a male, given that you got a B plus, 59 out of 120. And then we're looking for the probability of being a male in general. So it's 288 out of 653. So 59 out of $1.20 should be about a half, 0.492. 288 over 653, about 0.441. All right, so same deal as the previous calculation. It's in the neighborhood, but they're not the same. All right, close, but not the same. Later on in the course, I'll show you how we can determine if this sample information can be used to project out onto the entire population. But until then, we'll just say, nope, they're not independent events. So they are dependent events.